Hi and welcome everyone to this next session, which will be regarding Abaqus SimULIA from DSA. And with us we have Jan Granlund from DSA. He will be doing the presentation for us. Myself, I'm Finn Søgnen. I'm going to be the organizer.
So we can get started. Thank you for having me here. My name is Jan Granlund. I work for DSA Systems, located in Sweden, where we support our products and technology on the Nordic market. So the title of this talk is Realistic Simulation Made Easy, even if easy, well, it's not necessarily meant as neglecting the challenges that might be in using advanced simulations, but it's rather about getting the right toolbox to get you in a situation to create simulations easy. So the driver for us really in providing the simulation tools here is that we kind of think that what if we would have a robust nonlinear simulation tool? Wouldn't that really make us be able to make less assumptions and make more qualified predictions of the product behavior? And advanced simulation tool here means something that can take into account contact, that is how parts interact with each other, large deformations, buckling, instability, joining technology, failure, and so forth. And also to have a tool that allows us to do all the physics in a singular simulation environment, so that we can model and simulate the product in the real environment where we will see where the product will operate at the customer configuration. And having that, we package those in a brand called SimULIA from DSA Systems. And SimULIA is a brand dedicated to make realistic simulation and integral business practice, allowing to explore and discover and understand product life and nature. So this is kind of the overall drivers that we are working with. And with a target to, of course, reduce physical testing and as such save time, money, and improve quality. What we see in the current examples here are on the left-hand side, a buckling analysis presented by Japanese consultancy company, Mechanical Design and Analysis Corporation. And on the right-hand side of the picture, we see the side impact of a crash dummy, obviously for improving the passenger safety for all of us when traveling in cars around the world. So again, SimULIA is not a product, nor is it a company, it's a brand, and as a brand it's populated by a number of products. And this is what my talk here is going to circle around. So Abaqus is a product which has a number of analysis products, which I will cover in some detail. The interactive environment for Abaqus, pre and post processor. Some of the other products on the SimULIA brand, Eyesight for process management and optimization, Tosca for shape and topology optimization, and FE-Safe for durability assessment will also be presented in this context. Just before we get ourselves into the details, DSA Systems is a fairly big company, more than 20,000 employees around 133 countries. And we are in addition to SimULIA products, Dassault Systems is probably known for the CAD and PLM software like CATIA. SolidWorks is also part of our portfolio. So with that, let's turn our focus in a slightly different scale. We will talk about Abaqus, as I mentioned. So Abaqus comprises an interactive environment, Abaqus CAE, and some analysis of solver products, Abaqus Standard and Abaqus Explicit, which I will talk about in the next coming few minutes. So Abaqus is intended to provide simulation capabilities across a wide variety of application bases here, both for designers as well as for experts, and obviously also for different sophistication levels. So a complete set of simulation tool will of course be a big need for, let's say, more routine type of analysis, but many of our customers also see a need for more sophisticated types of analysis, where we see some of the multi-physics or crash events, which certainly falls into the category of very advanced or sophisticated analysis. Abaqus is a very general simulation tool, which have a very complete set of physics implemented, and as a result we have a very strong footprint across almost all the industries today. So as you can see some examples from in this picture, we have customers in almost any industry category. With that, I'm going to start to talk a little bit about Abaqus CAE, which will be the graphical user interface where you actually meet and create your models. Abaqus CAE is a modern graphical user interface. It's modular and well organized, easy to learn and use modern feature trees for navigation and so forth. It's a relatively young system. It was presented in 1999. We went Windows native in 2004, and development has been aggressive ever since. It offers, in addition to the modeling tools, native modeling tools, we offer good CAD interfaces for any customer who happen to already be in the possession of a CAD tool. So CAD can be imported and further operated on for suiting the simulation purposes. We also have a very powerful and complete meshing tool, fast and automatic free meshing for shells and for solids, semi-automatic hex meshing for solids, and tools to abstract away unimportant features with respect to simulation capabilities or simulation needs, really. It's also a very powerful visualization tool for managing even large results files. Transparency plots, view cuts, probing animations, and XY plots, and view cuts or whatever. So it's really the most popular visualization tool for our customer base across all industries. It is also built around Python as a journaling language and a scripting language. So Python scripts can easily be used to automate repetitive tasks, and we can also extend the graphical user interface. We can customize the system by using Python scripting. And Python scripting, for those not familiar with that, is a public domain language, so it's available to anyone, and it allows for partners to build applications on top of our products. So what we see here is an example. On the left-hand side is the kind of the out-of-box Abaqus CAE, and on the right-hand side we see a full customization where we have made a complete process of a knee implant simulator. We can make that fairly complex simulation process available to a wider audience by creating a customized GUI for that, so that the user can focus on the necessary input and automatically create, run, and post-process the results. So with that, let's turn our focus a little bit more to our analysis products. The solvers are modern, robust solvers, scales efficiently across multiple cores. Abaqus Standard was presented in 1978. Abaqus Explicit was presented in 1992. And the last major structural upgrade or migration to the current hardware environment was made in year 2000 to get us into file systems and databases consistent with the current hardware architecture. One of our strategic customers who we have been working very closely with our R&D is BMW, which I believe has demonstrated very well where simulation has become a very predictive activity. So they can substantially reduce the number of hardware tests and so forth, and have a great confidence in that the simulation results accurately predict the product behavior and performance. And I think this is where simulation will prove its value to anyone who decide to embark on the use of simulation here. So our solver products have an extensive library of material models, covers almost any material that's used in the engineering industry. In addition to the material models as such, we also have an extensive damage and failure modeling capability, both for bulk failure and interface failures. More specifically, the two solvers we have, Abaqus Standard, it's based on what is known as an implicit solution technique, which offers, of course, static simulation capabilities, but also dynamic capabilities. These simulations can be done under linear assumptions or nonlinear assumptions based on the requirements in the current scenario. So we see here a bunch of examples where Abaqus is used. Clip insertion, stresses in, for example, the bicycle frame, electrical fuse heating, sealing simulation, noise emissions from vibrating structures such as tires, sealing assessment, solder joint fatigue. These are all examples of common simulations done with Abaqus. Abaqus Explicit is a very efficient complement to Abaqus Standard. It's primarily intended for high-speed, very transient dynamic events, but can also be a very powerful tool for very nonlinear quasi-static events. Some examples are seen on this slide. Bottle drops. So this is done across many of our customers to ensure that the packages or juice packages or whatever will be able to sustain drop event without necessarily fracturing and spilling all the fluids across the floor or whatever. Manufacturing simulations, bottle conveying systems are all examples where Abaqus Explicit can efficiently be used. Contact is a very important aspect or ingredient in advanced analysis types, and it is numerically quite challenging to manage, but we have come a long way, and we have a general contact capability which is extremely easy to set up, so the user can select to just say that I have contact everywhere on all free surfaces, and just go ahead and run our simulations. More advanced analysis might be required to simulate the products in the real scenarios or the real environment. So to take that into account, the tool can naturally take into consideration, for example, that the turbine or an impeller is actually spinning at a quite high speed, which will affect the stresses and the stiffness of the structure. So the operating condition will have an effect on the eigenfrequencies, for example. So that will have to be taken into account when performing realistic simulation of those conditions. Damage and fracture is also oftentimes important for us to take into consideration in the design. Maybe most of the time we really want to make a design that should try to avoid failure, and in other circumstances we have to deal with the fact that things actually break and we see damage. And some extreme cases, as we can see on some of the animations here, we actually use the damage behavior to provide the product performance, like crash safety or energy absorption systems for that kind of purposes. Connector elements in the solver also provides for simplifying some connections to allow us to a little bit more cheaper do full system analysis, but also to include features like spot welds with failure criteria in them, or connector elements also have readily available pre-compiled connection like hinges or translators, which can be used to activate or drive a mechanism, all with the purpose of providing realistic simulation in the real environment for the products. Multiphysics analysis is also coming to become more important as we try to do realistic simulation. A large number of coupled analysis sequences are available in Abaqus as well. What we see here, for example, is a disc brake where friction will generate heat, of course, and heat will result in thermal expansion, and thermal expansion will affect the distribution of the contact stresses between the pad and the rotor. So this is a fully coupled system. electromagnetic heating, for example. Electromagnetic, the current will introduce heat, and the heat will then maybe introduce a change in magnetic permeability, and as such it will change the magnetic field, and so we need to run that in a coupled fashion. Fluid structure interaction is also oftentimes an important aspect in modeling the real environment for products, and there are a number of native FSI types of simulation capabilities within Abaqus itself. These are a couple of examples in Abaqus Explicit, where we have a coupled Eulerian Lagrangian formulation, and that is we can use an Eulerian formulation for modeling fluids or fluid-like behavior, and a conventional Lagrangian formulation for the tire here. Particle methods are also available, where that's an elementless method, so we have only nodes, which makes modeling quite a lot easier in some cases. What we see on the lower right-hand side is it's an impact, ballistic impact simulation, where the conventional elements based on failure criteria is converted into particles as required by the simulation conditions. Some technology we recently have been developing in the solvers environment has been with the purpose of providing simulation for additive manufacturing. So to support simulation of this kind of manufacturing process, we need to be able to continuously add material to our simulation domain. So elements can be progressively activated, and we can, during that process, calculate what are the free surfaces to provide the correct cooling, and also heat may be used in a simulation like a laser or so a moving general heat source can also be prescribed, and these are the most important aspects of providing a framework for additive manufacturing process simulation. I will return in a few minutes to discuss what this can be used for more efficiently. I mentioned that there were other products on the SimULIA brand, and another one is Eyesight, which is also our process management and optimization tool. So Eyesight is also in reality a software robot, if you will. So Eyesight can be used to drive other applications such as Abaqus. And as such, we can use that to integrate and execute one or multiple simulation tools. It can also be used to drive CAD projects and so forth. It also offers parametric optimization, so we can use that to perform design of experiments, optimization, and so forth. And as such, help us to provide a better overview of product performance across various operating conditions and various product designs maybe. So the real target with Eyesight is that typically simulation activity may involve geometry creation, passing on information to create the structural model and maybe a fluid model, and passing those results into another point where cost may be evaluated and so forth. With Eyesight, we could integrate and simplify this process to allow for many more iterations in the same time frame and reduce the risk of human error or mistakes, or which is usually a big risk when there is a manual process in transferring information here. Tosca capabilities is the non-parametric optimization that we offer. It comes in some different flavors here. So Tosca Structure Topology Optimization is the tool that allow to remove sort of the material, taking into account that there are some restrictions or design targets for stiffness and stresses and so forth to be met. So basically providing the lightest possible structure. Sizing is something which can be applied on, for example, thin metal sheet structures to optimize the thickness for various purposes, but of course to minimize the weight, but also take into account some other performance attributes of the structure. Shape optimization is usually accompanied or followed by topology optimization. That is, first the topology optimization provides a geometry, and this could be further refined by shape optimization, where we fine tweak the fillets and radius primarily for the purpose of increasing the durability or reducing the fatigue stress. Tosca bead is typically used for modifying the eigenfrequencies by adding beads, so that we shift the eigenfrequencies out of the critical excitation frequencies. Tosca fluid is something which you can attach Tosca to a CFD solver and come up with a topology optimization with respect to flow properties. FE-Safe is our application or product for assessment of fatigue. So this is typically something which we add on our simulation results. So FE-Safe will be able to read the stress results and potentially multiply that with some signal data, or in other circumstances, FE-Safe, the FE simulation upstream could actually contain a more representative reflection of the product's operating conditions, maybe a rotating object or thermal cycles, for example, that could be imported as such. And FE-Safe has a solid documented footprint across many industries as well. So with that, I'm going to turn my focus a little bit to talk about some trends in applications used with Abaqus that I have noticed more recently. We, as all of us, of course, notice there is a strong focus nowadays on sustainability and becoming more, reducing the environmental footprint, CO2 footprint, and so forth. And there is a very strong urgency here as well. So many of these changes are being pushed quite aggressively in the industry. And what I will talk about here are some examples of in cases where simulation can be a very efficient tool to assist us in making these transitions. So I touched on topology optimization earlier on, and with this example, I want to illustrate how topology optimization can be accessed easily with Abaqus software. So as an example, we have this brake pedal assembly here. So we see on the right hand side actually the full pedal assembly, but we will for this example here we will focus on the brake pedal as isolated. So we isolate the brake pedal here, and for topology optimization, these models are set up in a way that the geometry that we see on screen here is what we call the full design space, or the space where it's feasible to potentially have material. We can also, with some assistance here, identify some regions to be frozen as required by design, and that of course could be joints or locations which is connected to adjacent parts in the assembly. So in this particular example, we have the spots which connects the brake pedal to the upstream mechanism. Obviously, the brake pedal itself, where the driver would put the foot, that's maybe naturally, but this is also a frozen region, so we do not allow the solver to remove or change the amount of material that we have around here. This is known as an optimization process, and obviously an optimization process is done with certain objectives. And most of the time, topology optimization is done with an objective of reducing the mass. So basically, we are starting with a full mass of the design volume, and we can set a target for how much we measured from this state, how much we want the mass to be reduced. The optimization process will then also be defined with certain constraints. So in this case, we will have constraints on the amount of deformation on the brake pedal. We can also have constraints in the maximum allowed stress, for example, which is relevant, of course, because we don't want to overstress the choice of material that we currently have selected. So with those conditions, we can launch a topology optimization run. So this is an iterative process. So the solver effectively will run first the full model, and then it will identify regions where the stresses are low, and basically the strategy is really to try to take out material with small stresses, which subsequently will raise the stresses in other regions that will be conformed to comply with the limitations, the constraint we have imposed. So the animation here actually shows a number of iterations as we go through, and this is the end result meeting the specific requirements we provided for this simulation, and obviously it's eliminated a fair amount of material that will provide us to produce a cheaper and lighter product, of course. Another thing which I see a bit of a trend in terms of simulation is that we can there is a generally sort of an increased requirement for fidelity in the simulation, which makes it more and more relevant to include part of the manufacturing history. This is becoming obvious as we might change to new types of materials, we might consider different manufacturing processes, and doing this in a forced time frame doesn't really allow us to rely on many years of experience for establishing what would be the design criteria. So simulation is a very, very powerful tool here. A few years ago, commercial aerospace industry made the transition from mostly aluminum structures into composites, for example, and that's a good example where simulation then became a very important tool in order to help us to validate those designs. Additive manufacturing has also become a manufacturing capability that come into consideration occasionally. So these AM capabilities that we have developed for the software products, which I talked about just briefly recently, they can come very handy in including, for example, effects of welding simulations that may play an important role in the final state in terms of stresses and strains and so forth in our products. So let's have a look at what we can do in this context for when we design things using composites. There is an add-on capability into Abaqus CA, which in addition to the native composite modeling features, also can provide for taking into account the manufacturing process. So basically we can start building. We have the geometry depicted with a hemisphere here. We can take into account how the textiles in a composite would react to the draping that would occur during simulation. Obviously, if you take a unidirectional fiber or anything like that and drape it around your structure, it will shear, and the fiber or the orientation of the reinforcement in that material will change constantly. And this is a very powerful tool to take that into account and accurately predict the performance behavior. And as required, we can easily go back and change conditions at the production level to maybe we need to rotate this a little bit to come up with a better fiber orientation or material orientation for the structural performance of our product. This is a very powerful and it has become very popular in aerospace industry to speed up the interaction and contact between production planning and product performance assessed at the simulation level. Just one example here of some advanced features here which will have something to say about the ultimate properties here. You can imagine that if you have a more advanced or a more complex shape of your product, if we try to drape a textile or a cloth around that, there is a risk that it will wrinkle and behave weirdly. You can imagine when we're approaching Christmas and we try to wrap your packages, you know, that it's not always easy if there are anything other than a box that you are wrapping. So for these purposes, we can use, as one of the more advanced tools here, we can predict also where we need to make splits or basically cut this initially in order to avoid undesired wrinkles in a structure. I mentioned welding as an example where we could kind of backfit the AM simulation capabilities. So welding is in fact what we could call additive manufacturing process, in a way that we add material and we add heat into our model. So the additive manufacturing simulation capabilities that we have provides for ways of adding material into the mesh. So the technique is really that the elements are there to begin with, but the domains or the regions that are used for this process, the elements are initially empty. And we will gradually or progressively, we will add material. And for welding purposes, we use the polymer or the extrusion-like of material deposition. So basically, we just have a path where a nozzle, you can think of that as being a nozzle that will deposit material at a certain rate into the elements. The heat is subsequently also distributed into the mesh, following a path of the heat source, which in the case of welding, a flat plate like this is a relatively simple, just a straight line. The heat, we can prescribe then the power, of course, of the heat source. We can also define the distribution shape. It could be either a point, single point, or for a more detailed type of modeling, we can provide a distribution, a distributed shape, oftentimes known as Goldach distribution, that will automatically be intersected with the mesh. And there are continuity equations and so forth that will guarantee that we will deposit the correct amount of energy into the mesh. This kind of simulation comes in a wide range of different, I would say, fidelity levels, where the simplest one is a pure static analysis, where material, as it's deposited, could have what is known as an inherent strain or an eigenstrain, which is how welding simulations historically has been done. Or the most fully advanced type of simulation is where we do a full sequentially thermal mechanical coupling. And this is what we see on the left-hand side here, how the weld simulation here would be first a temperature simulation or thermal simulation where material is added, free surfaces is calculated, radiation and heat exchange with the ambient is taken into account. This would give us the thermal history. And once the thermal history is established, we could use that as a load and introduce that into a stress analysis. And the stress analysis will allow us to compute what would be potentially distortions to our structure. And also it would be able to predict the magnitude of the residual stresses that might be in the model after welding simulations. These distortions results could, if required, be used to compensate the geometry, if the structure warps or deforms. In some cases, we want to compensate the geometry for that. So we could bring that back into the geometry more or less and rerun the simulation and validate how a pre-compensated geometry would conform to the nominal measurements. All right, so this basically takes me to the end of my talk here. The Abaqus analysis product, as we have seen, provides for realistic simulation for all industries and all levels of users. We provide linear and non-linear behavior. We have sophisticated contact and material modeling. We have high-performance solvers to provide for short turnaround times. Abaqus CAE is an easy-to-use interface, integrates well with the popular CAD packages. It offers a comprehensive support for some solver functionality and also an extensive customization capability to provide routine workflows easier. So it's really a single solution for all analysis needs. So that takes me to the end of my presentation here. So if there are questions, I'll be glad to take them now.
Yes, thanks, Jan. That was great. Great presentation. There are a couple of questions here, and people can still ask questions using the questions panel. But let's see here. So, can I purchase a perpetual license, or is it subscription licenses only?
Well, both license types are available, as far as I know. So, yeah.
Okay, yeah, good. Another question here is, how do I determine the number of tokens I need to run 4 and 32 cores?
There is a formula for the token usage here, which is effectively the number of tokens is I believe to begin with at least 4 plus n, where n is the number of cores that you're using. So for a nonlinear analysis, you will use a single core analysis will use 5 tokens. A 2-core analysis will use 6 tokens and so forth. Then there is a drop off when you come to really high. So when you are about 20 cores, I think it roughly will use around 20 tokens.
Last question we have here is it possible to only add a viewer to a license if we are 2 users, but one doesn't need to run pre and post processing?
Yes, that's possible. Yeah.
Like I said, if any of the attendees have additional questions, you can send them into info@Alfasoft.com. thanks a lot, Jan, for your great presentation, and hope to have you with us next time we're running this ODD.
Okay, thank you.